I welcome you to this module of flow through porous media. What we were discussing was miscible displacement. That is, if one gives a pulse or one gives a step change in concentration at the inlet and simultaneously the flow is taking place at constant flow rate. So, what would be the mixing and what we expect at the outlet. So, this is something which we are discussing, and we have already established in the static system when we give a step change how it behaves. So, now we are going to convert that to the flow process. So, we are discussing about dispersion of solute or tracer in the porous media. This is something which we ended up with. This was the equation for a static system, and we said that when this C1 infinity can be set to 0, then this would be the governing equation. C1 as a function of z and time, it can be given as this into 1 minus error function. And what is this error function? Generally, it is customary to write this as C0 into complementary error function, since it is 1 minus something. So, it is customary to write complementary error function, that is ERFC z divided by square root of 4 dt. So, now we said that this is based on that C1 0 being held there as constant. C1 0 for all time t greater than 0, this is held at C1 0 and this is held constant. But when there is a step change and this step change is flowing through a capillary, we expect this concentration to be like here there is a build up. So, similarly there would be a depletion. So, we can assume this instead of this C1 0, it is operating as C1 0 to C1 0 by 2. So, that means instead of this as the profile, we are looking at this as the profile and this as the mirror image of this as the profile. So, this is something which we can work with. So, that is the right away what they said is that when there is a flow, we are not maintaining C1 0, rather anything that is diffusing to the downstream has to come from the upstream. So, any gain in the downstream is equivalent to loss in the upstream. So, concentration, if these and these are mirror images, instead of C1 0, we should consider this to be C1 0 by 2 straight away. So, that is why this half is appearing here. So, and we put there here one C bar, I mean it is just to remain consistent with what we had done earlier for tailored dispersion. In fact, that we will go there in a moment. Let us, I mean just make note that we are going to put a factor half for this reason, considering this to be an exact mirror image. And instead of a static system, when the front moves at an average velocity u bar, then z has to be replaced by z minus u bar into t. This we had done earlier for moving coordinate system. So, and further, when the velocity profile is laminar, now you make note here, I mean if I had this front to be perfectly uniform, that means this is the velocity front, every layer, the entire cross section is traveling with the same velocity, then we could have solved this in a different way. That means, we could have considered this velocity u bar as the exact velocity and the diffusion that is taking place, that is the diffusion, that is just the diffusivity, right. What we did last time, if you recall, in case of a Dirac function, when it is traveling, we said it can travel under two conditions. One is uniform velocity profile, that means velocity over the entire cross section is everywhere it is same. So, what that means is simply as if it is in a static system, only this system is traveling over some time. So, it is as good as giving this Dirac function some residence time in the static system, wherever it would have gone, the same thing would have happened, because there is no stretching of this, no parabolic velocity profile, no stretching of this pulse. So, it is as if this is remaining a static system, only it is given that residence time inside the capillary, so when it reaches the outlet, over that residence time whatever diffusion would have happened, that diffusion had happened there. So, this is one way of looking at it. Second, so in that case when we did this, that time we had written it as m divided by pi r0 square, which is m by a, then there was some term here, and then e to the power of minus z square divided by some term here, and this z minus we have considered the velocity multiplied by t whole square, and here wherever this d term is appearing here, or square root of d term is appearing here. So, these d term, this is just simple diffusivity, because it is under just simple diffusion, only it is, instead of sitting in a batch system, it is given the residence time. So, now we have hypothesized it as if I have given just the residence time in a static system, same as whether it is travelling through this capillary. Now, on the other hand, when this Dirac function is placed in a capillary where non-uniform velocity profile was set in by virtue of laminar velocity profile, where this pulse is stretched in the form of a parabolic distribution. In that case also, you remember, if you look at the final result of Taylor dispersion, we stuck to that same form of equation, m by a divided by some term involving pi dt and then e to the power minus z square, that some term is there, divided by some term involving dt, etc. So, this same form we maintained, only instead of d we had here Ez. Ez is the dispersion coefficient. Instead of d here we had Ez, which is the dispersion coefficient. So, now d is gone. Instead of d we are writing r naught square v naught square divided by 48d, that is the dispersion coefficient. So, they said that okay, at the outlet if we want to do this, the only change we have to do is we have to change the diffusion coefficient to the dispersion coefficient now, and obviously the velocity, this for the moving coordinate I have to use the average velocity. Here in this case, for uniform velocity it is same as velocity at every point is same as the average velocity. In case of parabolic velocity profile, velocity is not same everywhere, but one needs to consider the average velocity, so that they know that the center of this pulse, how far it is moving. So, what we essentially say here is that when velocity profile is laminar or parabolic, then d also has been replaced by this dispersion coefficient. Last time we call it Ez. Now, in case of a step change, the general literature says this is as dispersion coefficient for capillary. Okay, so, dCt, which is same as r, basically radius of the capillary square, average velocity square divided by 48d. So, and further there is one point I must note here, that the Taylor, beyond Taylor, Aris, who is the next scientist who worked on it, he showed that if somebody wants to consider axial diffusion, you remember when Taylor did this analysis, that time we considered axial convection and radial diffusion. But Aris showed that on top of this, if one considers axial diffusion also, then simply that Ez term or the dispersion coefficient term, that term will where there you have to add simply one d to this r square u r square by 48d, so that this would be capable of including the effect of axial diffusion. So, this is something which Aris has shown. So, that is I mean that is up to somebody if they want to consider axial diffusion or ignore the axial diffusion, that choice is there. So, now finally, what one ends up with is this C bar. Now, we are calling it C bar. I mean, I do not, I'm assuming there would be Taylor dispersion inside the capillary. So, Taylor dispersion inside the capillary, only thing is I have, instead of Dirac function, I have given a step change. Okay. So, now there in that case we had a concentration profile by Taylor dispersion. for Dirac function, for a pulse, for a step change, we are arriving there. Also in case of a Taylor dispersion, we talked about C bar, and C bar was a function of Z and T. Why C bar? Because we had averaged it over the R, right. We said that concentration profile in radial direction is of no use. So, over the entire cross section we will average it. So, that is why instead of C 1 as function of R Z T, we move to C bar Z T. So, and that was equal to this form we had discussed in the Taylor dispersion. So, now in this case we have this same C bar, but for a step change in concentration is equal to half into C 0. This C bar, there also we had a C 0. So, here also it is C 0. So, C bar divided by C 0 is equal to half 1 minus error function of Z minus U bar T, the moving coordinate system has to be set in, divided by square root of 4 dCt this time, which is the dispersion coefficient for a capillary, multiplied by T. So, this is the final expression. This is the final expression for concentration profile for a step change in concentration in a capillary. So, just like we have a final expression C bar, actually there the C naught does not make sense. So, that is why we had this m by pi r naught square, because there m matters in case of a pulse. How much kg you have placed, that is important. So, m matters. So, that is why it is written as m by pi r naught square. So, you have a form in case of a Taylor dispersion which relates C bar Z T in the form of, but there we had an exponential term. Here instead of exponential term you have error function, but same C bar we are relating, instead of m by pi r naught square you are having C naught, half C naught 1 minus error function of this quantity. So, now this is something which we will carry forward when we go to porous medium. This is something, because we have a, or rather we can take that also, we can continue with that exercise as well. But if you are working with a step change, in fact this is truly speaking, you can use either of these. One is just put a pulse. So, for that what would be the stretch or spreading of that pulse, and otherwise you put a step change and continue and see how much. So, I have given a step change here, and after the residence time I see the step change is showing like this. So, how much it has, how much is the spreading, how much the front is smeared. So, this is something we can see. So, now we have now seen how to do these two things. One is Dirac function to spreading or step change to spreading. So, how we can analyze these, for a capillary. So, these are the two expressions. This is one expression, and the other expression we have discussed in a previous lecture. So, now we can look at, let us say we said C bar by C 0. So, we can plot this C bar by C 0 as a function of, we said we have choice for the x axis, two choices we have. One could be simply time, or it could be the volumetric flow rate multiplied by time. Volumetric flow rate multiplied by time. So, this could be the x axis or this could be the x axis. And people have taken it further, they said, okay, why volumetric flow rate multiplied by time will give me the cumulative volume. Okay. So, instead of that you divide it by the pore volume, so, or void volume in that for that particular medium. So, what this gives me now, number of pore volumes. If you divide it by the pore volume. So, what is the idea here? That So then if we put as number of pore volumes, or people generally shorten it in and say that pore volumes. Okay, pore volumes means what, how many number of pore volumes. For example, if this material has a volume of, let us say, 0.001 meter cube and it has a porosity of 0.1. So, total volume, let us say overall volume is this, and porosity is equal to 0.1. So, then one can say that 0.0001 would be the pore volume. So, instead of plotting it with point this way, what they do is, when say let us say I have injected 0.0005 meter cube. So, instead of calling it 0.0005 meter cube, I call this as equivalent to 5 pore volumes. That means 5 number of pore volumes, 5 pore volumes. So, now if you plot these as effluent produced in terms of pore volumes and C bar by C 0, moment we do it C bar by C 0, C 0 is the change in, you remember, I mean we had talked about C 1 bar and C 1 0, right. So, if we do this, then we expect that this will be scaled in that case. It is scaled between 0 to 1.0 moment you, so this becomes dimensionless, right, because your C 1 0 is the concentration that can be the maximum concentration it can reach. So, because the step change was from 0 to, we are assuming 0 to C 1 0. So, then it is C 1 bar by C 1 0. If we plot C 1 bar, so this any concentration at any point, this is C 1, this is the average concentration. So, when you divide it by C 1 0, then automatically this becomes, this is normalized within this 0 to 1 scale. So, now essentially if we had given a step change, we expect that at V p is equal to 1, that means at 1 pore volume, you have that 1 pore volume means you have just, that is equivalent to the residence time, that is equivalent to the, if this was the overall volume and this is the porosity, 1 pore volume is equivalent to 0.0001 meter cube. This is this point. So, I expect if there is no smearing, nothing, it is just a plug flow and no mixing, nothing, I would have expected it was all 0 and suddenly boom, it is 1.0 and continuing. But because of this mixing, which we have already accounted through this fixed second law and all, we would expect that these lines will be smeared. And how much smeared? It depends on, of course, the dispersion coefficient, that is what we are interested in. So, it depends on dispersion coefficient, and in this context there is a dimensionless number which is important, which is called Peclet number. Peclet number is equal to convective transport divided by diffusive transport. What are the contribution of convective transport to that of diffusive transport? So, it can be written as 2 r u bar by d. So, u bar is the average velocity which is the flow is taking place, and diffusive transport d is the diffusion coefficient. Okay. Similarly, one can think of a dimensionless time tau, which is equal to T d by r square. So, this is also a dimensionless. This term is dimensionless, this term is dimensionless. This term is referred as Peclet number. So, these lines, they will vary, I mean depending on the value of Ez or depending on the value of Peclet number. I mean either way you can think of it, that these lines will change. And so, basically if one has a porous medium is given and then somebody runs such type of a test. Suppose there is a core given and they were asked to run a test. So, one can very well put 2 reservoirs. One reservoir has let us say, if this is a sandstone core, generally it is customary to inject not just direct water, but some amount of salt to avoid any clay swelling inside this. So, let us say you have 1% NaCl, which was inside it is 1% NaCl, and then same 1% NaCl was flowing, and then you have another line here for 2% NaCl. So, let us say this is 2% NaCl, and this 2% NaCl also can be injected, and there is a valve, and then suddenly at one point you simply turn the valve, so that instead of 1% NaCl, now it is 2% NaCl which is being injected. So, instead of 1%, now it is 2% NaCl getting injected. So, essentially you have provided a step change in concentration, and at the outlet you are collecting fractions. That is possible, or there are some instruments where this flow can be directly fed into that instrument, and instrument will continuously give the record with time. So, either way, so one can get these concentration values at the outlet. So, if somebody plot these concentrations, one can get this kind of a plot. If they let us say this change from 1% to 2%. So, if you can make this dimensionless, that means in this case what do you have? In this case you have C1 0 is equal to 2% and C1 infinity is equal to 1%. So, you can find out what is the so you have here we are writing it as C1 bar minus C1 0. Instead of that, you can write it as C1 bar minus C1 infinity divided by C1 0 minus C1 infinity. So, you can make this is also dimensionless. If you have, because here C1 infinity is 1%. If you are not working with sandstone, if you are working simply a pack of glass beads, this kind of glass beads, these are used for electroosmotic pumping, for micro when one needs pumping action at a very low flow rate by applying a voltage. So, those are so in case, so suppose one is going for electroosmotic pumping and where these are filled with glass beads instead of sandstone and water is just fine, then in that case C1 infinity would be 0. So, C1 infinity would be 0, it is 0. So, it becomes C1 bar by C1 0. So, this is what you are working with. So, now if somebody quickly measures this value and find out. So, they are registering, they are recognizing this, they are measuring this C1 bar with time. So, that is what against fractions, they are collecting fractions and everywhere they are measuring C1 bar. So, they are finding this ratio and plotting it. So, we expect this ratio to turn to from 0 to 1 near about this location Vp is equal to 1. So, one generate, let us say someone with an unknown core plug they have generated this plot. Okay. So, now one can go back and use that equation that we have already shown. We have already shown an equation, right, which was half of 1 minus error function of this we just discussed before, half into 1 minus error function of z minus u bar t divided by square root of 4 dCTT. So, this is, so everything is known. I have a profile, only unknown here is this dCT. So, by looking at this concept, so these are experimental measurements at this time now. Okay. So, these are experimental measurements and we know what velocity this fluid is being injected and at the outlet at a given time what are the concentrations. So, only unknown is this dCT, and so if this only unknown is this dCT, in that case one can find out what is the dCT that corresponds to this particular profile. What is the dCT that corresponds to this particular profile? Okay. So, now I have, this is one plot and then for another one, another core, another similar core you have, there you saw that this was the profile. So, for this new profile, new one, you can have a different dCT. So, instead of looking at the profile, you can directly look at the dispersion coefficient and then compare which one has more dispersion inside, that is more mixing inside the porous medium, and which one has less mixing. And coming to think about this mixing, if you will, I must point out, suppose I see a profile of the C bar by C 0 versus V p, the number of pore volumes, and it came like this. Let us say this is let us say 1.0. So, this is 1.0 and it came like this, and I know from the measurement of porosity that one pore volume comes here, and I see a profile something like this in for an unknown porous medium. So, what in that case my immediate conclusion would be that there are some hypermeability streaks or some channels existing, some hypermeability zones existing inside the core, and so flow is not uniform or flow is not as we have thought in case of a homogeneous porous medium with bundle of capillaries. There are some zones through which the flow is taking place faster. Okay, so by looking at these plots, I can make lot of make lot of judgments about the quality of this porous medium, whether it is homogeneous, whether it tends to whether it will lead to more mixing. So by looking at those numbers, by looking at that DCT value. So these are some of the elements that we need to think about when we do this miscible displacement. I will continue this exercise. Now we have already covered most of the fundamentals of dispersion process. Now we focus only on dispersion in porous medium. Exactly what are the trends? Okay, so that is something which we are going to address in the next lecture. So this is all I have as far as the present lecture is concerned. Thank you very much.